All righty, let's go ahead and get started. So, just to let you know what's going on with the rest of the semester, it looks like we have today, we have next week, Monday, Wednesday, and Friday, and then the following week we'll have Monday. So, what I'm planning on doing is working backwards that Monday, so not next week, but the week after, we'll have our final exam review. And so we'll discuss all the topics we've gone over for the whole semester, let you know what you can expect for the final exam and all of that stuff. The Friday before that, so this coming Friday, next week, will be our last test before the final exam. So that test, of course, is on optics, light and optics, the topics we've been discussing lately. That'll be our third test for the semester. The Wednesday before that, so this coming Wednesday, will be our exam review. So the test 3 review to prepare for it. And then today and Monday, we will finish up discussion on light and optics. So that's basically what we have coming up today and Monday. Finish optics. Wednesday will be exam 3 review. Friday will be exam 3. And then Monday, the following Monday, will be the final exam review, our last day. And then, of course, the final exam will be whenever the final exam for our particular class is scheduled. I don't have the date on me right now. I'll bring it with me next week. But if you do want to know what it is, if you're curious, I know the little final exam schedule was sent out by email to everyone by the registrar. So go ahead and take a look. Just look for when is the final exam for Monday, Wednesday, Friday classes at 1 o'clock. And it'll tell you what day our final exam will be. But again, I'll bring it with me next week that way, and I'll say specifically when it is. But this is kind of the plan for the rest of the semester. So we're just going to finish up talking about optics, basically finishing up this topic of refraction, work some example problems on it, and then prepare for the test and then the final exam. So with that said, let's go ahead and keep discussing about refraction. Refraction, if you remember, is the bending of light. So light travels in a straight line. It just keeps on going until, of course, it runs into something. Unless, of course, it goes from one material to another material. So for instance, the sunlight coming in, traveling through the air, and then it hits the lake or a pond or something. And so it goes from the air into water. And because different materials allow light to move at different speeds, the change in the velocity of light when it goes into a new material makes the light change its path. It changes the angle that it's traveling in the material. And Snell's law is the equation that allows us to calculate how that path will change. And what Snell's law says is n1 sine theta 1 is equal to n2 sine theta 2, where n is called the index of refraction. And if you remember what the index of refraction was, it's a number. Each material has its own number. And it's basically a measure of how fast light moves in that material. So in air, the index of refraction is 1 because it moves at the speed of light. But then if it's in water, it's 1.33 because now it moves a little slower in water than it did in air. In glass, it's 1.5. It moves even slower in glass than in air, and so forth. Theta, of course, there's two thetas because we are talking about two materials. You're going from air to water, let's say. Theta is the angle that the light is traveling through with respect to what's called the normal. The normal is that line which is perpendicular to the surface. So if you have a pond, the surface of the pond is horizontal. You make a little vertical line, an imaginary vertical line where the light hits the pond, and you measure the angle with respect to that. Okay, that's the technicality of it. At the end of the day, it's just the angle that the light makes with respect to the surface. And one thing we know is that if light travels from a less dense medium to more dense medium, the angle will get smaller. That is, the light bends towards the normal. So if the light was coming in at 30 degrees, it bends inwards, and now it may be at 20 or 22 degrees or something like that. And then, of course, the opposite of true. If we're going from a more dense medium like glass to a less dense medium like air, well, now the angle will get bigger. All right, so that was the theory we had. So let's work some examples. Make sure we know how to use Snell's law appropriately. So here's an example. Here's the surface. Let's say this is glass and this is air. Light's coming in. It comes in at an angle of, let's say, 40 degrees. And so it'll bend. I assume it's going to bend towards the normal because I'm going from air to glass. I'm getting into a more dense material. And so I'd like to know, what is this theta 2? What is the angle of refraction, theta 2? Well, in order to do this, one thing we need to know is what's the index of refraction of our materials? Okay, this is something given on the test, so you don't have to memorize them. But for these, air, n is equal to 1. And glass, n is equal to 1.5. All right, so there's our setup. Light's coming in from the air, hits some glass. Maybe this is like a glass table or a crystal ball or something. Light's coming in, hits the surface at this angle, and you want to know when it travels through the glass, what's the new path going to be? What's the angle of refraction? And so we know anytime we talk about refraction, Snell's law is the guy. So N1 sine theta 1 is N2 sine theta 2. There's our equation. Generally speaking, I make the side with all the ones, the first material, obviously, and the side with all the twos, the second material. So for this problem, the one stuff is air and the two stuff is glass. So just plug my numbers in. N1, 1. Sine theta 1, well, theta 1 is the angle that the light makes in the air, which is 40, is equal to N2, well, that's the glass, so that's 1.5, times sine theta 2. Theta 2 is the thing I'm trying to calculate. That's the angle of refraction. So pretty easy, just one unknown sitting here. We do the algebra. Sine theta 2 is equal to 1 divided by 1.5 times sine of 40. But again, I don't want sine of theta 2, I just want theta 2. So I take the inverse sine of both sides, And that leaves me with theta 2 is the inverse sine, sine minus 1 on your calculator, of whatever this number is, 1 over 1.5 multiplied by sine of 40. And so now I get my calculator out. Now, I've already seen it this semester with this class and a previous class and another separate class I'm teaching. We're also doing optics in that class. And I see it every semester that I teach this. Typing this in your calculator can be risky because it's easy to make a mistake without knowing you're making a mistake. The calculator interprets things weird sometimes. So you have to be careful with parentheses and stuff. So what I suggest, which is what I do personally, even though I have a lot of practice with my calculator, I don't trust myself. I don't try to type all of this stuff in at once. You can do it. And in fact, if you type it just like this, you'll get the right answer if you keep the parentheses and everything. But sometimes you may miss a parentheses. And so the calculator thinks, oh, it's 1 divided by 1.5 times sine 40. But actually the sine of 40 is supposed to be on the top. And so you'll get a different number. So what I do is I just do this one step at a time. So I'll talk my way through what I'm typing. I do 1 divided by 1.5 and I push enter to get a number. Then I multiply that number by the sine of 40 and I get a number. Now with that number, I do the inverse sine of that thing and I get the angle 25.4. Okay. So if you try typing this in your calculator and you don't get this number, there's one of two issues. Either your calculator is in radian mode. And what we're doing here, we're using angles, we're using degree angles here. So use degree mode, not radian mode. The other issue is if you try to type it in your calculator, you don't get this number, then there's something you mistyped somewhere. Even if you don't think you mistyped it, like I said, the calculator may assume one of the things should be in the denominator when it's actually in the numerator or whatever. So try typing it one step at a time and see if that helps. That usually solves the problem. And that's what has helped me to make sure I reduce the mistakes I make on my calculator as much as possible. Also, I could look at the answer and see if it makes sense. Here, the light is going from air to glass. So I'm going from a less dense to a more dense medium, which means I'm going to expect the angle to get smaller. Well, the original angle was 40. Now it's 25. It did get smaller. So that seems all right to me. If this angle had been 55 degrees, then I know I did something wrong because the angle shouldn't have gotten bigger, it should have gotten smaller. All right, so any questions about this example? All right, I guess you're feeling confident. So let's work on a more complicated question. This time we have 3 materials instead of 2. So let's say we have air, water, and then glass. Okay. And what happens, of course, light's coming in, hits the surface of the water, and it bends inwards. Okay. Then that light hits the surface of the glass. So of course it's going to change directions again, and it'll bend inward one more time. So what do I have? Let's say the light's coming in at an angle of, I'll use 60 degrees in the air. And what I'd like to find out is this theta 3, what is the angle of the light in the glass? Given the index of refraction of air is 1, water is 1.33, and glass is 1.5. So there's my complex question. I've got a refraction problem. Light is coming in from the air. It hits the surface of water. It then travels through the water and hits the surface of glass. The question is, what will be the angle of refraction in the glass? All right, so how do we handle this? Now we have multiple layers. We don't just have the single layer problem like before. Now we have two separate layers. Well, we use Snell's law. What we can do is this. The roadmap in my mind goes this way. I'm going to forget about the glass for a second, because what I'd like to do is say, if I want the answer in the glass, then I can say, okay, just pretend that the light's coming from the water to the glass. So I'd like to do, n2 sine theta 2 is n3 sine theta 3 and calculate theta 3. The problem is, I don't know what theta 2 is. I don't know what this angle is here, theta 2. I know the angle in the air, but I don't know the angle in the water. So in order for me to use this equation, I first have to calculate the angle that's in the water. How do I do that? Snell's law. Start in the air. N1 sine theta 1 is N2 sine theta 2. So if I go from the air to the water, that'll tell me what theta 2 is. And then geometry says that theta 2 is the same as the theta 2 going from water to glass, right? If we think about geometry, if you have a horizontal line and a line like this, a diagonal, geometry says this angle theta is the same as that angle theta. So same goes here. The angle from air to water is the same as the angle from water to glass, because it's just a horizontal line with a diagonal line on it. So that's my plan. My plan is I want to use Snell's law to go from water to glass to get the answer in glass. But to do it, I first need to know what is the angle in the water. So use Snell's law from air to water to get the angle of the water. Then I could use it to get the angle in the glass. Okay, does that make sense? Any questions about the concept, the thought process? Okay, so I hope it's intuitive. So let's do it. Let's go ahead and work this out. Let me get rid of this really quick. Say, all right. First step, think about air to water. Air to water. So we have N1 sine theta 1 is N2 sine theta 2. In the air, N is 1, sine of 60 is equal to N2, which is 1.33 sine of theta 2. So solving this for theta 2 is inverse sine, as always, of 1 over 1.33 times sine of 60. So 1 over 1.33 times sine of 60, inverse sine of this answer, I get theta 2 must be 40.63 degrees. All right, so any questions so far? Going from air to water, I used Snell's law, and I found the angle of refraction in the water. Any issues with this piece? All right, well, now that that's set up, now I could go from water to glass. So now I'm here. This is my line. I'm going in the water. I already know my angle is 40.6, and I'm going to hit the glass. So N2 sine theta 2 is N3 sine theta 3. The 2 stuff is water, the 3 stuff is glass. So N2 is 1.33. And sine of theta 2 is 40.63. Is equal to N3. This is the glass, 1.5 times sine of theta 3. But theta 3 is the guy I've been trying to find this whole time. That's my unknown. So perfect. That's the only unknown here. Do the little algebra. Theta 3 is inverse sine of 1.33 divided by 1.5 times sine of 40.63. So again, calculator, 1.33 over 1.5 times the sine of 40.63. Inverse sine of this answer tells me theta 3 is 35.26 degrees. Now, let's see if this makes sense. The first step, I went from air to water. So I'm less dense to more dense. And my original angle is 60, so the angle should get smaller. What do I get? 40. Perfect. It's smaller, seems okay. The second step, water to glass. Again, less dense to more dense. So my original angle is 40. The new angle should be something less than 40. 35. Perfect. It's less than 40. Seems to make sense. So I can be confident I likely did all the math here correct. Any questions about this? Now, obviously, if you have more layers, you just do more Snell's law stuff. Another layer gives you another Snell's law. But I have good news. Even though this works, and this is perfectly legitimate, and this is how you should do it, there is a faster way. There's a shortcut. Okay? Now, does anybody happen to see what the shortcut is? Remember, you have these 3 layers. You're going from air into the water and then into the glass, and you want to know what's the angle into glass. What we did was we did Snell's law from air to water to get water's angle, and then Snell's law from water to glass to get glass's angle. There's a faster way to do it. Can anybody guess, figure out what a faster way of doing this might be? Any thoughts?
Could you have factored it?
What do you mean by factor it? Factor what?
Like, remember the first examples you were showing? Like, I have all the signs in one, and then we square it, but that would be more efficient versus like.
Oh. Yeah, so that's with polarization stuff. Here, we're not squaring anything. So with the first, the stuff you're talking about was the law of malice, where you have cosine squareds. There's nothing squared, so there's nothing like we multiply it first and then we square it after kind of a thing. Here's the shortcut. Here's the secret. And when you see it, it's going to make complete sense. But it's one of those things, it's like someone smart had to come along to show all of us idiots. And it's like, how in the world do we not see this? Think about the steps we're doing. We're first doing N1 sine theta 1 is equal to N2 sine theta 2 to get theta 2. And then we do N2 sine theta 2 to give us N3 sine theta 3. Right? That's what we did. But this is stupid. Because if I rewrite it slightly easier to see, I can say this is the same as saying A is equal to B and B is equal to C. Right? N1 sine theta 1 is A, N2 sine theta 2 is B. And then n2 sine theta 2 is equal to n3 sine theta 3. Well, notice if A is equal to B and B equals to C, then all we have to do is do A and C. This implies A is equal to C. Because if A is B and B is C, then it must be that A is C. So instead of doing all this business, all I have to do is n1 sine theta 1 is n3 sine theta 3. And skip the water altogether. Because if n1 sine theta 1 is n2 sine theta 2, then instead of writing n2 sine theta 2 again, just write n1 sine theta 1 is equal to n3 sine theta 3. Okay, does that make sense? Can everybody see that this is true? Good, good, perfect. So this is nice. What this means is if you have a problem like this, where you have multiple layers, and the problem is asking you only for the final answer, and you don't care anything about the middle, we'll just go straight from the beginning to the end. If you had 10 layers, you just do n1 sine theta 1 is n10 sine theta 10. And all the stuff in the middle doesn't matter. Now, there is a technicality about this that I'm glossing over. There is, if you're actually doing this, because of a topic we're about to talk about related to this, there's a possibility that things get messed up in the middle based on what angles we choose. But besides the technicality, this would work if you're given a problem on a test or homework that's multiple layers like this. And the only thing I ask for is the final angle. Then you could just do the first layer is equal to the last layer, just like this down here. Now, if I asked you for both, if I said, what's the angle in the water and what's the angle in the glass, then yes, you have to do it the way we just did it. Now, this is true for everybody. We're all in science, even though you may not be going into physics as a career, you're in a scientific field. And the number one characteristic of a good scientist is to not believe anything you hear. Okay, prove it to yourself. Even though you're learning, you're supposed to be learning from me, you shouldn't just believe what I say. You should show yourself that this is true. And that's true about all experts you listen to. Any expert in any field, if you have the ability to, you should confirm what they say. Okay, so let's confirm this is true. If what I say is true, then we should be able to do this and get that answer, 35. So let's try it. N1 sine theta 1 is N3, oops, and not M, sine theta 3. So we're starting in air, 1 times sine of 60. Going to glass, 1.5 sine theta 3. Solving for theta 3, we get inverse sine of 1 over 1.5 times sine of 60. So let's see, 1 over 1.5 times sine of 60, inverse sine of that angle, and I get 35.26. Indeed, the same answer. So I claimed you can do this and it would be fine, mathematically speaking, and I just proved it. Yes, you can either do it the full-on traditional way of you do Snell's law for the first layer to the second to get the angle in the second layer, and then use Snell's law from the second to the third layer to get the last angle. Or we could skip it, do the shortcut method, and just go from the first to the last layer straight, and we'll get the same answer. Of course we do. The logic makes sense. If A is equal to B and B is equal to C, then it must be true that A is equal to C. And that's what I did. So keep this in mind. When you're on a test, and let's say the test is timed or something, and you have a big, long, complicated question like this, and you're afraid you're going to run out of time, if it happens that all the professor wants is this final angle, you don't need the stuff in the middle, then do the shortcut. You'll save yourself some time. You don't have to do the shortcut. You can do it the traditional way. That's perfectly fine too. Either way, it's just Snell's law. Now, we've seen Snell's law traditionally, one layer to another. We've seen it with multiple layers. There's one more thing I want to show you about Snell's law. Let's look at this example, an interesting example. Let's say you're going from water to air, okay? And we're going, our light hits, and it hits at an angle of, let's say 60 degrees. Okay, well, firstly, if I had to draw the problem, how do I think the light's gonna go? Well, water is more dense than air. So I'm going from more dense to less dense. The angle should get bigger. So I think the light should get this way. So this angle is bigger than the original angle. I'll call that theta 2, the angle of refraction. Okay, so just like the nice, simple Snell's law problem, a 2-layer problem going from water into air, let's do it. Of course, as before, index of refraction of water is 1.33. Index of refraction of air is 1. So Snell's law, N1 sine theta 1 is N2 sine theta 2. Someone work this out and calculate the answer for me. I'll start writing down the work, but try calculating it yourself and tell me what you get for theta 2. 1.33 sine of 60 is 1 times sine theta 2. And just go ahead and pipe up when you get an answer. Anyone have an answer yet?
I think my calculator's in radians mode. Do you know how to take it out? Because it's giving me error.
Error? That's weird. Yeah, if you, so what kind of calculator do you have? You have a Texas Instrument, a TI something?
Yeah, 84.
Yeah, so at the top of your calculator, next to the blue second button, or I don't know what color it'll be, the second button, there's a button called mode. You click on mode, and then one of the options in there says degree or radian. You just make sure it's highlighting on degree. Is it in degree mode or is it in radian right now?
Yeah, it was in.
Okay. Anybody else? Surely not everybody is just laying in bed taking a nap right now.
Mine keeps saying error. I took it out of radian and I keep getting domain error.
Yeah, mine's too.
Huh, that's very interesting. And it's completely not surprising at all to me because it should give you an error. How do I know it's going to give you an error? Well, this is a technicality about math. But if you get something sine -1 and the number you're trying to plug into this thing is bigger than 1, so I think you get like 1.15 or something, this is impossible. Because what it says is there's some angle, you take the sine of that angle and you get a number bigger than 1. But we know from trig, if you remember, the biggest the sine can ever get is 1. So what that means is there's something wrong with this problem. There's something that doesn't make sense or it doesn't work or something. So the fact that you're getting an error is good. It's perfect. I wanted you to get an error. You're not doing anything wrong. The reason is this. There's a phenomenon when light bends, and we can see it if we think about what this looks like. Let's say we're in the water down here. You're underwater with a laser pointer and there's air up here, and you shine the light towards the air. Well, if the light comes in like this, well, we know that light bends away from the perpendicular, so it's going to bend like that. And then if the light comes in like this, it's going to bend even more. Well, notice eventually you get to a point where this angle down here, whatever this angle is so big that it actually is 90 degrees. It runs along the floor. And so if you get bigger than that, it starts to reflect back down. It actually doesn't go into the air. And it's because the angle the angle the light would be making is bigger and bigger and bigger. Eventually it gets so big, it's bigger than 90. So it reflects, it doesn't go into the air. This is a phenomenon which is called total internal reflection. And what that says is, under the case where you're starting in a more dense medium and you're going to a less dense medium. Okay, so it's not every time, but only if you're going from more dense to less dense. So like for this problem, we're going from water to air. Then there will be some angle big enough where the light does not go into the air, but rather starts to stay in the water. It reflects back down. Okay, for angles smaller than this, it'll go into the air. Angles bigger than this, it reflects. This angle is what's called the critical angle. That's the exact perfect angle where the light does not go out, it does not reflect, it just travels along the surface. Okay, an angle bigger reflects, an angle smaller can leave. This is a very interesting thing, and I mentioned it at the end of last class, but this is what allows us to do things like fiber optics. When you see all these fiber optic decorations and things, well, it's just a piece of glass filament. Glass, of course, is transparent. So the light from whatever color wheel or whatever is in the decoration should be able to travel into the glass and then just come out like it's traveling into water. It should go into the air. But because it's at a special angle, instead of going out into the air, it just reflects back. Here it's doing it from the water to the air. In fiber optics, it's like a glass to air, same type of thing. So the problem with this example is that the angle that the light traveled in the water originally was too big. That angle is bigger than the critical angle. So instead of the picture looking like this, what really would have happened is the light would have reflected back into the water and would not have gone into the air. That's why you don't get a θ2. There is no θ2. It stays in the water. There is no light going into the air. Even though you're like, well, that's weird. It's just water. It's not being blocked. It's not a wall. It's not a mirror. There's no reason the light shouldn't just leave the water and go into the air. But the way these things work, the way the light bends, makes it so, in fact, if the angle is big enough, it will act like a mirror. So that's the last topic I want to discuss. Total internal reflection and the critical angle. Let's say we want to calculate the critical angle for water. Is this the theory behind one-way mirrors? No, I think that I don't think so. I think one-way mirrors they spray a special coating that allows light to travel one way and not the other. I think that's a different effect. I don't know personally the reason they work, so I don't want to guess because I could just be giving you bad information. But I don't believe one-way mirrors work by this effect. Because if it did work by this effect, then some of the light would get through because some of the light would be at an angle smaller than the critical angle. Like if you're looking directly straight. So for instance, if I had water down here and air, if the light went straight up, well, the light's just going to go right through. If the light goes this way, it'll go through. But if it's way over here, then it'll reflect. So if that is how the one-way mirrors were working, there would be sometimes the light gets through because the angle is small enough, and other times it reflects because it's too big. But with one-way mirrors, it always reflects on one side. And so I don't think it can be this. Unfortunately, I can't give you better information about why, but that's all I know for sure. So let's say this was our question. We want to know, oh Lord, this is an important thing. If I want to send a signal, let's say I'm underwater, maybe I'm a ship, a submarine, or you're just playing around, you got friends over at a pool, and you want to test this out, then we would want to know, okay, how, at what angle should I shine my light? Well, the way you would do it is you say, okay, critical angle for water, that would mean I'm starting in the water and I'm going to air. There must be some angle, this angle I'll call theta C, the critical angle, that I shine my light, and it just perfectly shines so that instead of going into the air and instead of reflecting, it just skims the surface. Okay, that's the critical angle. Bigger than that, that's when it starts to reflect. So this is like the extreme point. And so the question is, what is this theta C that this occurs? Well, if you look this up in a textbook, the textbook would say, oh, that's easy. Theta C is sine minus 1 of N2 over N1. Okay. Now, I'm not going to use this because I confuse, is it N1 over N2 or is it N2 over N1? I'll show you, so you don't think you have to memorize an extra equation, that this is just Snell's law. Let's solve it with Snell's law. N1 sine theta 1 is N2 sine theta 2. So critical angle for water, that means I'm going from water to air. So water is the one stuff, air is the two stuff. If this is the critical angle, then water, that's 1.33 for N, as always. Theta 1 is what I'm trying to find, so I'll call it theta C for critical angle. So I'm not looking for theta 2 anymore, now I'm looking for theta 1. And the air stuff, well, N2 is 1. Now, what do I put for sine of theta 2? What is theta 2? Theta 2 is the angle the light makes in the air. But if this is a critical angle, I told you, the light doesn't go into the air, it skims the surface. Well, all that means is the angle is 90 degrees. Because if you look at how the light makes a light beam and the normal line is vertical, well, there's 90 degrees between them. So it always is true that when you're calculating the critical angle, theta 2 is 90 degrees. So 90. Now when I calculate it, I see, okay, sine of theta c is 1 over 1.33 times sine of 90, but sine of 90 is 1. So calculate theta c is inverse sine of 1 over 1.33. And now you see where the textbook gets their formula. They start with Snell's law and they solve it a little bit for you and then gives you the last bit. But in my opinion, this is my thinking, especially in the times where you need to learn your own equations and all of that, I always hated when I had 3 equations, but really it was just one equation solved different ways because I'm trying to memorize them like they're different things and I have a bad memory. But to me, if all I have to do is memorize one thing, Snell's law, but Snell's law can give me everything I need, we'll just learn that. So I start with Snell's law. The only rule you have to know is that if we're talking about the critical angle, then theta 2 is 90 degrees. And so you solve that for theta c or theta 1, and you'll get your answer. I believe, what is it for water? I think it's something like 48.7 degrees.
I have a question.
Yes, ma'am.
So when it's drawn like that, we always think of it as the critical angle and then use Snell's law, no matter what the first angle is, theta 1.
Okay, yeah, so critical angle is theta 1. So basically what I'm doing is I'm setting up a problem. Let's say this is an experiment and you're under the water and you're shining your little laser pointer towards the air. Well, what you're going to do is you're going to shine it and then you're going to move the laser pointer, changing the angle little by little until you reach a certain angle where now the laser pointer just skims the surface. At that point, your theta 1, the thing you're doing, is now called theta c. It's now called the critical angle. So in these examples over here, you know what the angle is that's coming in and you're trying to figure out the light that's going out. With this, when we're talking about critical angle, you're trying to find what the first angle is. What should be theta 1 in order for this effect to occur? So theta 1 is your theta c, but it's only theta c if your theta 2 happens to be 90 degrees. So you force theta 2 to be 90, and then you say, what should be theta 1 that does that? Okay.
Okay.
So that makes,
yeah, that makes more sense. Because I thought the critical angle was the 90 degrees.
yeah. I get that happens a lot for sure. Yeah, it's just a nomenclature thing. The critical angle is the angle you shine the light to make it so that the light doesn't go into the air. So technically what it means is, what angle should you shine a light to make theta 2 90 degrees? That thing is called, what is the critical angle? So in this case, theta 2 is 90. You know what theta 2 is, and you're trying to find theta 1. Yeah, good.
Thank you.
You're welcome. Any other questions about this? All right, I'll just mention, because class is over, I'll let everybody go. What I was talking about before, where if you have multiple layers, there's a technicality where things can mess up in the middle. This is why. Because you can have a point where you go, let's say, instead of going from air to water to glass, I did air to glass to water. Well, air to glass, no problem. But going from glass to water, I'm going from a more dense to a less dense medium. If I set up the problem wrong originally, so that once the light goes from the air into the glass, the angle of the light in the glass part is too big, it's bigger than the critical angle. So the light will never reach the water. It'll just reflect. So that's why I said earlier, we can always do this little shortcut thing, except for the technicality where things could mess up if I'm not careful. That's why. You have the ability for, depending on what the layers are like, there's a critical angle somewhere that makes it so the light just stops. It doesn't actually keep going through. But unless I make a mistake making up problems on your test, I'm not going to do that. And that has happened. I remember one year, one of the final exams, I wasn't careful and the problem did work out that way. So everybody was getting an error. And so I had to say, oh my God, I had to change the numbers while we were taking the test. So don't think I'm going to give you a problem like that where you have to worry about it. But I did want to say, just to be clear, while I say we can just skip and do the shortcut, there are times where you have to be careful about such things in the real world. Anyway, that's it for today. Monday, we will do some more examples on refraction, do some more examples on critical angle, make sure we have refraction down. Wednesday, test review. Friday, the last test on light and optics. And then Monday of next week, our last class will be our final exam review. So that's what to expect. Be sure you've worked on the homework. I think it's due Sunday. It's polarization homework. So be sure you're working on that. I will post a refraction homework as well, just so you can get a good look at what a problem would be like on a test. So be sure to check Canvas for any assignments. And of course, when I do post the assignment, I'll send an email just to remind you. But yeah, check to make sure if you haven't already done the homework, you're working on them. I believe the next one is due Sunday, and then there'll be one due next week as well for refraction, just for the practice. Other than that, if you have no questions, you are free to go and enjoy the rest of your day. I'll see you next week.
Have a nice day.
All right, you too.